Alrighty. Hey there. So we're going to go over the answers to the review sheet. We got to test it a little bit. The first question everyone wants to ask is, during the test, do I get to use the periodic table? Yes. Very good, Julie. Very good. Really proud of you. Yes, Francois. An extra purple packet? Yeah, there's purple packets over there by the goggles if you want to borrow one. I'll pass the periodic tables out right before the test. I don't trust Billy over here. He would write all over it as we're going over things. You don't get to use your own periodic table, Josephine, because you have all sorts. Look at these adorable things that she is all over. Look, that's so cute, right? I don't know what this pattern is, but there's too much information on here. That's sound effect of an actual periodic table. There's too much information on here, and that's not fair because what should I call you? Lily doesn't ever write anything down on her periodic table, and you're just too advanced for her. So everyone gets the same boring laminated periodic tables. The names of the elements are the same. There's just nothing on them. See, that's slightly different sound effect. Sorry, that's so loud. What's up? Yes. It just records the screen. Yes. So they're listening to my voice, and they get to see me draw fabulous pieces of artwork as I talk. Okay? No, that hadn't been recording then. We're good there. Okay. And we're back from pause. Okay. So the first thing was the scientists. Hopefully you've studied the different scientists that we talked about, so you know who did what. Democritus is the guy who came up with the term for atom. He was just kind of sitting around Socrates thinking about the world and realized there's got to be a smallest piece. Let's call it the atom. J.J. Thomson did two things. We scratched out Kelvin's name, and now that's kind of weird that Thomson and Thomson both appear. The plum pudding model was Thomson, and the cathode ray tube was also Thomson. So who's this other Thomson? It's the same guy. Sorry, bad form. Let's just blame it on the guy next door and move on. What did J.J. Thomson discover when he was studying with cathode ray tubes? The electron. And after discovering the electron, he decided since there's a negative, there's probably a positive. I just can't find it yet. And bless yous. And then eventually, that was a sneeze if you didn't hear that. Eventually, he decided, man, there must be some form to matter, and he came up with the plum pudding model, which was a big positive goo with electrons jammed into it. What else? John Dalton had his 5 atomic theories. He said the atoms that are identical, atoms that are different. Atoms combine together to form compounds, and during reactions, they rearrange. And over here we have Ernest Rutherford, who played with gold foil. And after he played with the gold foil, he realized there must be a nucleus because he was shooting these positive charges at the gold foil, and they kept going through. So they were missing the positive charge. He deduced that the nucleus was a tiny, tiny, tiny positive charge. And James Chadwick discovered the neutron, which sounds really anticlimactic after all the other things. What is a cation? What is anion? Bad joke. Cats have paws, therefore cations are positive. Yes, I just recorded that joke. A negative anion, AN ion, A negative anion. Anions have the negative charges, cations have the positive charges. Number 3 was the easiest question people didn't know what to do with. It was literally saying you have a phosphorus and 3 chlorines. What would it be? 1 phosphorus and 3 chlorines. 2 borons, 6 hydrogens. 2 borons, 6 hydrogens. Just write the formula based off the number of each element and do nothing else. Yes, Lily Angela. The difference between the molecule and a compound is very subtle at this point right now in the year. Molecules are nonmetals held together by something called covalent bonding, which we haven't done yet this year. And compounds are metals and nonmetals held together through ionic bonding, which we haven't really done yet this year. So those two terms aren't what really matters. What matters is that this has 6, 12, 6. This has 1 and 2. But we're going to get into next chapter, the chapter after that, why they're like that. When we're writing formulas right now, they're the exact same thing. Yes, uh-huh. Rainbow Bright, that's your nickname. So the question is, with a molecule like CO2 or CBr4, do we have to put a 1 there? You don't have to put a 1 there. Most chemists don't put a 1 there, but you could. You could say P1Cl3, or you could just write PCl3. The 1s are generally implied. Okay, Rainbow? All right. No reason for her nickname to be Rainbow, but that's what I did. Okay, number 4, you pull out your periodic tables. You find this stinking element Pu, and you look it up. When you look up Pu on your periodic table, let me grab a periodic table. On the periodic table, it says Pu 94. And then above it, it says something else, but we're going to ignore that. What does the 94 on these elements mean? The protons. The protons, right. So I grabbed all of the proton values right off the periodic table. I went Pu is 94, americium's 95, actinium's 89, cesium's 55, iridium 77, manganese 25. Then we have the neutrons, which is what I think Jimmy over there was trying to ask me about a little while ago. How do I find the neutrons? Good question, Jimmy. So on each of these symbols, there's also a mass. The mass is the protons plus the neutrons. Ergo, which is Latin for therefore, 244 for plutonium equals 94 plus what? And you have to solve for the missing neutrons through this magic of subtraction. Yes, feel free later to grab a yellow calculator in the back of the room for the test. You don't have to do that subtraction in your head. You can just grab a calculator. So I subtracted, and I got the neutrons, the neutrons, the neutrons, the neutrons, the neutrons, and the neutrons. Hey, Mr. Murphy. Yes, Jimmy. I notice on the periodic table that there are already masses. Like for manganese, it says 54.9380. Good question, Jimmy. That value there on your periodic table is actually an average of every manganese we've ever found on the planet. All we care about in this question is manganese 56, one of the many isotopes of manganese. It's not an average of all the manganese. This is one type. Your periodic table averages them all together because if you grab 100 manganeses, those 100 would be an average of all the manganese already. So we're not going to use the masses on our periodic table for much of anything. The protons we would. Lastly, what does this term here mean? Ooh, I'll use, what's this color? It's like kind of purple, but not. What color is that? Thank you, Susie. Pink. I would have said lavender, but okay, pink. It is uncharged. If it's uncharged, does that mean they're giving it to you for free? No, that means that the protons and the electrons are neutral or equal. Yeah, they're canceling each other out. So whatever the protons are, the electrons are the same because it's uncharged. These, therefore, if they're uncharged, are atoms. Atoms are neutral. What do we call them once they've gained or lost electrons? Once they're charged, they're no longer atoms. They're called ions, right? You keep your eye on the electrons. Once the electrons have changed, they'll be called ions. But these have not changed, so they're atoms. Number 5 was pretty much the same thing. I was writing the mass, the protons, the symbol. The mass, the protons, the symbol. In fact, I even had an example completely worked out. I was like, okay, here's A, Z, M. A is the mass, Z is the protons, X is the symbol. If Z is 8, it's oxygen, because the protons are 8. The mass would be the protons And the neutrons added together, what is 8 plus 9? Good job, Susie. It is 17, which is why I have 17 written down there for the mass. There's the protons. There's the symbol. So I just went through, bam, 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 hit each of those. Perguntas estudiadas aqui. You have any questions about number 5? Good, Lucy? Yeah, okay. All right. All names in today's video are fictitious. Well, not fictitious, just not the right names. 6. What's the difference between a mass number and an average atomic mass? I think I literally just said this. The periodic table is the average of all of the masses together. It's not one isotope, it's all of the isotopes. Where a mass number is just one type of isotope. You could almost look at it as the average atomic mass is Johnny's mass. There's Johnny in the back there. Johnny's mass for his entire life, the average of his entire life. Is the mass you are today, Johnny, going to be the same as you are 2 years from now? No. You're going to go to college, you're going to put on 15 pounds like most college freshmen do, and your mass is going to change. But you could take the average of all of you and then list it. This is the average Johnny mass. True? The periodic table is the average mass of all of one element on the entire planet so far. Number 7, how did Rutherford's gold foil experiment show that there was a nucleus? He was shooting these particles at them. They were positive particles, these positive alpha particles, and they went right through the gold foil, and they weren't hitting anything. And if they're not hitting anything, there must not be much in there to hit. So the positive particles weren't hitting the positive, so the positive had to be very tiny. He was missing it. 95% of all the particles went straight through, so he then deduced that there must be some tiny positive thing in there. He called it the nucleus. There's only... Wait, strike that statement. Chlorine was the only one that was a little bit tricky. And that's because I didn't tell you the charge or the electrons. That was kind of evil. But let's talk about all of the others before we talk about chlorine. Atomic number is really what? Protons. Good job, Johnny. Really protons. So this is proton, 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 proton. Sulfur on your list? Is this one? Oh, it's just a freebie thrown on there for extra fun. The electrons could be gained or lost. Has this nitrogen one gained or lost electrons? No, its charge is 0. See, 7 and 7 make 0. Well, what do you mean? Now, 7 and 7 make 14. I agree. 7 positives and 7 negatives add up to 0. So when you're talking about the protons and the electrons, imagine them as tiny positives and negatives being added together, and then you can approach the charge from a different perspective. So let's talk about tin. Not 10, tin. Tin, SN, go to the periodic table, it's TIN. It's 119 for its mass, positive 4. I go to the periodic table and I find this out pretty easily. I have the mass, because there's the mass. How did I know it was 46? How did I get that 46? You subtract electrons. A positive charge means electrons have been lost. So when you lose a negative, your life becomes more positive. And I made a human being analogy in one of my classes. I said, imagine you've got a whole lot of people in your life, but one of them's super negative. If you remove that person from your life, cut them out of your life, your average happiness accidentally goes up in a very kind of weird way, doesn't it? Because you subtract a negative person from your life, then your average life is now more positive. That's really kind of a weird statement, and you should try to help them deal with their issues. But no? Okay. All right. I would. So the other way you can look at it, again, is you can just throw the charges in there. 50 positives, 46 negatives. What is 50 and 46 negatives added together? Plus 4. How did I get the neutrons, Jimmy? Oh, he said I don't know. He gave me the shoulder shrug of I don't know. The mass equals the protons plus the neutrons. So here, the mass is 119. It was literally given on that right there. The protons were 50. 119 equals 50 plus what? And you can solve for the neutrons. Cool, Jimmy? Good for the neutrons? All right. Does anyone ever watch that cartoon anymore? Is that even a cartoon? Jimmy Neutron? Oh, that's probably a good idea. It wasn't that good of a cartoon. Okay. Any others here you want to ask me about? Oh, the chlorine. I didn't give you a charge, and I didn't tell you the electrons, so there's a lot of possibilities. Back there, you were Lily, weren't you? All right. Lily and Rainbow were talking about this ahead of time, and Lily said, well, if this was an 18, then over here this would be a -1. And then Rainbow was like, but I put it down as a 17, and that's a 0. Well, I didn't give you enough information to really make a decision, did I? Sorry about that. It was totally Jimmy's fault. So I need to either give you a charge or the number of electrons, don't I? Yes, Susie Q. Number of neutrons? So atomic number is actually an old reference to the protons, directly just to the protons. The neutrons can change depending on the isotope you're talking about. So carbon is probably the most common one we talk about. Carbon always has 6 protons. That's the definition of carbon, 6 protons. Yeah, I just want to make sure I was right. I looked at the periodic table. 6, right? A lot of times carbon has 6 protons and 6 neutrons, so its mass is 12. Occasionally it's 6 protons and 7 neutrons, so its mass is 13, 6 and 7. And very rarely it's carbon 14, which is 6 and 8. But all 3 of those have different neutrons, but they still have how many protons? 6. They always have 6 protons. Okay. All right. Next thing. The math. No questions about this, so we'll just go to the next question. Just kidding. I can almost see the stress in my first period's class right now. So in this question, the first one, we knew the masses of 2 isotopes. They were mass 40 and mass 39, and we know the average. So we approached it from an algebra perspective. We approached it from an algebra. I just recorded that. From an algebra perspective, I said, if there's only 2 isotopes, and I am 20% of the stuff, then Lily would be 80%. She would be the rest if there's only 2 of us. True? 80 and 20 add up to 100. So that's how we approached this. We said if there's one mass and another mass, there's only 2 masses, then one percentage and the other percentage add up to 100. X, 100 minus X. If this was 20, this would be 100 minus 20. What's 100 minus 20? 80, yeah. So it would work out. So we set it up in an algebra style. 40 times X plus 39 times 100 minus X all over 100 equals the average. So on the right side, we have the average. The average better be between 40 and 39, and it is. And now we have to go through the algebra. And this is where people struggle because algebra was a thing some of you did a long time ago, and maybe you were great at it, or maybe you weren't. Maybe you made a very happy face like this one, or maybe you didn't. But the way I would do this is I would distribute that 39 through both of those values. That's what's going on here, 3901, 39.01x. And I would also move this 100 To the other side, I would multiply that by 100. So now it's 3931. And then I would combine like terms. I have 40x minus 39x. What is 40x and minus 39x combined together? 1x. And then you got to subtract this non-x value to the other side. And this one worked out pretty nicely. It was 1x equals 30. So what's the value of x then? 30. If I'm 30, what is Lily then? 70. She is the 100 minus x. She is 100 minus 30. She's the rest. So the one value is 30%, the other value is 70%. We didn't like those questions very much. We did a whole lab on them with pennies and things. Number 10 is the same idea, except we're given the percentages. I'm going to hide this for a second. I should have hidden it a second ago, but it's too late. There we go. So here's the setup. We have mass, percentage, mass, percentage, mass, percentage. And we're adding the masses and the percentages together after multiplying. After you add it all up, then you can divide by 100. This is called a weighted average. It's weighted by percentage. Why are we doing it by percentage instead of standard just count, add, divide? Because when we talk about atoms, you're not talking about 1 or 2 or 5 or 7. You're talking about billions and millions and trillions, oh my. So this might actually be 32 million that are 48. And 40 billion, dillion, dillion, dillion. So there's lots of them you're adding together, so we have to work by percentage. What do all percentages add up to, though, when you add all the percentages together? 100, which is why we're dividing by 100. So when I average them all together, ba-bing, does that answer make sense? Is it inside the range? If I average Lily's mass and Rainbow's mass together, Lily weighs like 75 newtons and Rainbow weighs 85 newtons. What's the average of 75 and 85? In between, right? If I accidentally said 75 and 85, the average is 14, you'd be like, you don't know how to average. That's not in between the two numbers you're averaging. So is this number inside the numbers we're averaging? It is. The numbers we're averaging are 48, 49, and 50. And that's in between those three numbers. Susie, no, you're not Susie. Let's call you Angela. Lily Angela, okay. I'm not going to be harping on sig figs with this question because there's so many moving pieces. And if you are in the realm of 49.24-ish, I'm going to be like, smiley face. Yes, ma'am. Oh, you know, there should be a unit on there, shouldn't there? Epic fail. Sorry. Let's switch to pen mode. The unit is the amazing atomic mass unit, AMU. And you can grab that unit right here. It's on each of the masses. It's hiding up there. Is the same question back there? Yes. Yep. And when we I'm going to make one thing clear. When I multiply the mass times this percentage, I'm multiplying it by 32, not 0.32. Okay? Because usually when you do the percentage, some people convert it to a decimal immediately. Well, the reason they're converting it to a decimal is they're dividing by 100. Well, we're going to do that afterwards. You could, if you were Johnny in the back. Johnny in the back could do 48 times 0.32, 49 times 0.12, 50 times 0.56, and add them up. And then he doesn't have to divide by 100 because he already has. But if you're going to divide by 100, leave these as their whole number selves, not their decimal selves. And the last thing was about radioactivity in half-lives and stuff. This graph, I'm trying to estimate the half-life. We went from 10. What's half of 10? 5. So that's about 5. Bing. I think this would be 30 right there. So it's between 20 and 30. I said between 25 and 30. Do you agree with that estimate? It's not perfect. Can't do much better with the way this graph is written. How long would it take to get to 1.25? Well, we've gone from 10 to 5. What's half of 5? 2.5. What's half of 2.5? Yep, that's the 1.25. Bing, bing. That's about 90, isn't it? You don't have to make those sound effects, okay? I could tell that you were wanting to make the sound effects. That would actually be really annoying during the test. Make them in your head like you usually do. On the curve, mark the different locations. So I've marked where all the half-lives occurred. Okay. Any other follow-up questions? Because we're out of questions on the worksheet, aren't we? You dropped that over there. We'll call you Nathan, because that would be funny. Because that's not your name. Anybody else? All right. You got periodic tables and a calculators? Let's go. Periodic tables and a calculators.